So let's start with a quick introduction. Nicholas Copernicus, born in 1473 in Poland, studied law and medicine, but his passion was astronomy. And he grew up in a world where the Ptolemaic model ruled. The earth was considered the center of the universe, and the heavens moved in perfect circles. So imagine being the only person questioning that widely accepted idea. And this geocentric model was reinforced by Aristotle's philosophy and even linked to Christian teachings about heaven and hell. So questioning it was a huge challenge. Next, Copernicus proposed a revolutionary idea. The sun is at the center of the universe. This is what we call a heliocentric universe. Helio meaning sun and centric means at the center. So in this system, Earth rotates on its axis and revolves around the sun. So this simple shift in perspective allowed for a much clearer understanding of planetary motion. But how did this new model explain the planet's retrograde motion? So this retrogression motion puzzled astronomers for centuries. It's when a planet appears to stop and move backward in the sky for a short time. And Copernicus explained this elegantly. Earth moves faster along its orbit than the outer planets. And as Earth overtakes Mars, for example, Mars seems to move backward from our perspective. Think of it like driving past a slower car on a circular racetrack. The car appears to move backward temporarily, and that's the retrograde motion. Now let's look at this diagram. You can see Earth passing Mars. This yellow line shows the apparent path of Mars as viewed from Earth, forming a loop during retrograde motion. So can you imagine looking up and seeing that motion? That's what astronomers observed. And Copernicus' model make it easier to explain than Ptolemy's complex epicycles. So here this diagram shows how Earth's motion makes the outer planets appear to move backward at certain times. So the Copernican model was revolutionary because it was simpler and more organized than the old Ptolemaic system. All planets orbit the sun and their speeds depend on how far they are from it. Now let's see how the Copernican model compares to the Ptolemaic model overall. So this system made it easier to understand planetary motions and removed many of the complicated loops and epicycles that the Ptolemaic system needed. However, Copernicus still assumed uniform circular motion. That means he assumed planets moved in perfect circles. So he still had to add small epicycles to match observations. So as a result, the model was not significantly more accurate than the old system for predicting exact positions. So here you can see the Copernican universe with planets moving in circular orbits. So notice how the planets closer to the sun move faster and the outer planets move slower, which makes the system look neat and ordered, much simpler than the tangled epicycles of Ptolemy. Now let's see how this simple model didn't just change astronomy but also how people thought about Earth and its place in the universe. So the Copernican hypothesis didn't just change how we understand the solar system. It changed how humanity sees itself. By placing the Earth at the center, Earth became just another planet orbiting the sun. So this idea went against centuries of thinking. People had to reconsider philosophical and religious views about Earth being special or fixed at the center of the universe. At first, astronomers liked the elegance and symmetry of the Copernican model, but they didn't fully accept it because it didn't perfectly match observations. But over time, the simplicity and symmetry helped gain wider support, leading to what we now call the Copernican revolution. And this revolution set the stage for later discoveries by Kepler and Galileo, whose work confirmed and expanded on Copernicus' ideas, which we are going to explore in the next section. Now let's study how planets actually move. So planetary motion puzzled astronomers for centuries. So let's explore how Tycho Brahe's precise observations and Kepler's genius solved the mystery. So last time we saw Copernicus put the sun at the center, moving Earth out of the center. And that solved the place of Earth problem. But planets were still tricky. So here's a question for you. If Earth moves, how do planets move around the sun? Do you have a guess? And observers noticed that planets sometimes move backward in the sky, called retrograde motion, which Copernicus couldn't explain fully. So think about it. If planets orbit the sun, shouldn't their motion be smooth? So people assumed planets move in perfect circles at uniform speeds, but observations didn't match. And this puzzle lasted decades. Now this mystery took another century to resolve. Thanks to two astronomers, Tycho Brahe, who made precise observations, and Johannes Kepler, who analyzed them mathematically. Now let's first meet Tycho Brahe, who collected the data that made everything else possible. So Tycho was not a priest like Copernicus. He was a Danish noble with a passion for math and astronomy. Even though telescopes didn't exist, he measured planets with amazing precision using large instruments. Imagine trying to measure stars without modern tools. How would you ensure accuracy? For example, when Jupiter and Saturn nearly merged in the sky in 1563, Tycho realized all tables were way off by a month or several days. So in 1572, a new star appeared brighter than Venus. And Tycho measured it every night and saw no parallax. So it stayed in the same position relative to the background stars. But classical astronomy said the heavens never changed. And Tycho measured the star's position carefully. So no parallax means it was farther than the moon. And this challenged Aristotle's idea of an unchanging sky. Therefore, Tycho combined accuracy with geocentric ideas. The sun and moon orbit Earth, but planets orbit the sun. So this is called the Tychonic model, a mix of old and new ideas. So how is this different from Copernicus or Ptolemy? Now look at this diagram of the universe. Earth is at the center, like in the old Ptolemaic model. But see the sun. It orbits Earth. Now can you trace the path of Mars? Does it go around the sun or Earth? Suppose and trace the path of the other planets. So other planets orbit the sun. Now did you notice how it's different from a fully Copernican system? And Tycho's observations were precise and crucial, but he didn't analyze them mathematically. So that's where Kepler comes in. So Tycho's observations provided the foundation for Kepler's analysis. Now let's meet Kepler. So Kepler was very different from Tycho. He grew up poor and sickly, but was brilliant with numbers. And he loved patterns and math, which made him perfect for analyzing Tycho's data. So Kepler saw patterns in the planets' orbits. So can you think of patterns in nature that repeat, like the seasons or phases of the moon? So even before meeting Tycho, Kepler believed in the sun-centered model. And he tried to explain why planets' orbits had certain distances using geometric shapes. So he tried fitting planets' orbits to geometric solids. Mysterium cosmographicum or mystery of cosmos. Although most of this was incorrect, it demonstrated his ability to think mathematically about the cosmos. So look at this model, which shows his early geometric model. Each planet's orbit fits around a geometric solid. Blue spaces indicate the sizes of the orbits of the planets with special geometric characteristics. So this drawing only shows Kepler's model for the orbits of Mars, Jupiter and Saturn. We know now that this is not how planets' orbits are actually spaced. But Kepler's attempts to make his model work showed that he was a gifted mathematician. So Kepler joined Tycho in Prague to work with his extremely precise observations. After Tycho died in 1601, Kepler inherited the data and became the imperial mathematician. So using this data, he studied Mars motion because it had noticeable retrograde motion, perfect to understand the real path of planets. And then he began discovering the true nature of planetary orbits. So imagine trying to figure out planets' motion just from the numbers. What kind of challenge would that be? Now let's see what Kepler discovered about planetary motion. So Kepler discovered that planetary orbits are not perfect circles. They are ellipses with the sun at one focus. So this was revolutionary. So what happens to a planet's speed if its orbit is stretched like an ellipse? In an ellipse, the distance to the sun changes as a planet moves. So this figure shows how an ellipse can be drawn with two tacks and a string. Imagine the pencil moving along the string. That is similar to how planets move around the sun. Even though most of orbits are nearly circular, Mercury is noticeably more elongated. This explains why planets sometimes appear to speed up or slow down in the sky. So next, Kepler's second law says that a line connecting the planet to the sun sweeps out equal areas in equal time. So when a planet is closer to the sun, it moves faster to sweep the same area. And when it is farther, it should move slower. So think of a roller coaster. When climbing up, it slows down, and when descending, it speeds up. And the sun's gravity affects planets similarly. Now let's discover Kepler's law in planetary motion. Now Kepler noticed a simple pattern. The farther a planet is, the longer it takes to orbit the sun. And this equation shows it mathematically. The square of the planet's orbital period is proportional to the cube of the semi-major axis of its orbit. So here P is the orbital period in years and A is the average distance to the sun. Now for example, Jupiter is 5.2 astronomical units from the sun. So can you calculate its orbital period P? Take a moment and give a try. First, let's plug in the numerical value for A. Average distance to the sun from Jupiter, which is 5.2 astronomical unit. Now let's take the cube, and that is 141. So 5.2 cube is 141. Now this is period square. So to find the period, we have to take the square root, which is approximately 11.9 years for its orbit. So the period of Jupiter is 11.9 years. Now imagine a planet twice as far. So how long would it take? Think about it, okay? So the Kepler's third law allowed astronomers to relate distances and periods. Now Kepler shared his findings in Astronomy and Nova in 1609, abandoning the 20,000-year-old idea of uniform circular motion. Now can you imagine convincing everyone that the Earth is not the center and Orbits are not perfect circles. But his laws were empirical, meaning they describe what happens without explaining why. But later, Newton explained the why with gravity. So, as a summary, Kepler turned careful observations into precise laws. So, next we will see how these laws let astronomers predict planetary processions with amazing accuracy using the Rudolphian tables. So, Kepler's Rudolphian tables combine his laws and Tycho's observations into a precise model that could predict planet positions far more accurately than ever before, up to 100 times better than previous tables. So, why do you think accuracy was so important for sailors and astronomers at the time? So, these tables showed that the sun centered system worked. Observations matched predictions, giving strong evidence that the model worked. And that gave a strong proof that Copernicus and Kepler were right. And these tables influenced future astronomers and paved the way for Newton to explain why planets move in ellipses. So Kepler solved planetary motion mathematically, even though gravity had not been discovered yet. Amazing, right? And Newton later explained why they move that way because of gravity. So while Kepler was perfect in the mathematics of planetary motion, Galileo was pointing a telescope at the heavens for the first time. So his discoveries gave direct evidence for the Copernican system. Evidence so strong that it led to both fame and conflict with the church. So let's look at Galileo's telescopic observations and his famous trial in the next section.